So what do we expect to get when we do this on average? So 5 heads, 50-50. And did most of you get that? Not by my count, right? So it looks like over 80% of you failed in this. And, and we would attribute this to what? I always like to suggest it's to incompetence, but this is what we call sampling error. And it's a very common type of error in data, and it's an easy one to deal with. So for the coin flip, most of us did not get the expected 5 heads of 10 flips. This is a type of variation around a mean. It's not the only type, but and when I say a mean, I mean an average. But you might call this noise or chance. They all mean the same thing. Okay, last time I said bias was a systematic difference between the true data and what you observe. Here, sampling error is not systematic. It's variation around a mean. It arises when events are determined by an underlying rate, say in this case probability of heads is 0.5, but we can't observe the rate. We can only sort of count individual events. Now, I'll go through a list of things that we attribute chance to, but we can think of this as chance is often a convenient model to describe our ignorance of underlying details. So basically, if we could measure everything, right, if a physicist could measure things, they could tell you whether the coin would come up heads or tails if they knew the force involved, the torque, etc. But we don't know those details, so what we end up doing is just describing it to chance. Well, about half the time it'll come out one way, half the other. Examples of sampling error and chance in our lives. There are many, right? And so this is not exhaustive. Obviously, gambling and games of chance. lottery would be one, card games, etc. Right? There, we're trying to beat the odds usually, but we understand there's a huge element of chance in the outcome. In medicine, disease and cancer incidence, we would say there's an underlying rate, but the number of cases we observe is subject to sampling error. You know, we talk about our chance. What's your chance of getting a certain type of cancer, right? We're talking about sampling error, and there it isn't certain that you'll get it. You can't get it at 30%. Either you're going to get it or you're not. And so we're describing this with sampling error. In many of your lives, you will experience sampling error in whether you get sons versus daughters. The odds are approximately 50-50, and there have been kits sold in the past that ostensibly allow you to change those odds, and they've been taken off the market by the FDA because they were frauds. Sampling error shows up when we count the number of people at events. Whether it's a football game, whether it's attending class, whether it's a grocery store, such, stores have to deal with the fact that there's a certain amount of sampling error. There's not a constant rate of people showing up, and sometimes they won't have enough people at the checkout stands to cover, everyone in the store at the time. Other times they'll have people, just employees standing around doing nothing. We also attribute to chance many unique events in our lives. And I'll put unique in quotes. So if you drive to school or ride a bike, there's some chance you'll get a flat tire, and that may happen once in your career at UT. It might happen several times, but there's some, that may happen, it may not. And whether it does or not, we attribute to sampling error. Accidents, we're well aware that there's a certain rate of accidents, and going on the road statistically says there's some chance they're going to be involved in a wreck. There's sort of a personal example of mine that I cite often. There's a friend, actually I think it was probably the first friend I had. I remember when I was 3, he was, I guess, the first kid in the neighborhood where we were growing up. And we went through high school together, and then I pretty much lost track of him, although I visited him once, and that's when he told me about this story. So we're in high school, and his dad had a store downtown, and he sometimes handled the store. And there was one occasion when 2 guys asked him to go celebrate this kid's 18th birthday. So back then, this were in the 60s, yeah. The drinking age was variable across counties. This was actually very common in states. And for beer, I think the drinking age in my county might have been 21, but the next county it was 18. So this friend of his had just turned 18, and they decided, okay, let's go, celebrate his birthday. We'll go drinking beer at this place, whatever. And so there was a driver and his friend, and they were going to pick him up at the store that evening when he closed. And so he was closing up the store, but to do that, he had to go into the back room and put some stuff away. And he was expecting these people to come by and get him. Anyway, he came out, as he came out the front door to lock it, he saw him turning the corner. And he waved, tried to get him, and they missed him, so they went off and had their celebration without him. And that night they were both killed coming back in the car. And so, and he told me this story, and of course he's telling me because he's realizing that just for absolute dumb luck, he wasn't in that car. And he almost certainly would have been killed if he had been, judging from the wreck. And so this is a case where, if we did this 100 times over, he would have been in that car many of those times and then presumably killed. And so we say it's just chance that on that occasion, he wasn't in the car. Even though not really chance, right? You can go back and say, well, there's a reason why he wasn't there. We know why he wasn't in that car, but in terms of predictability, in terms of describing this, we say well, that was just happened that way. We talk about chance. So that's a common model we use to describe the fact that if we repeated things over again, they wouldn't turn out the same way. Anyway, that's kind of an anecdote. What I want to focus on for the rest of the lecture is how we fix it and how we measure it. So, fixing sampling error. How can we reduce it? So you look at our distribution. I mean, you flip a coin 10 times, you realize there's a big chance you're going to get really far from what we think the true value is, which is 0.5. If you were doing this, you were aware of the sampling error, what would you do to decrease the distance between what you observe and the true value? Okay, a larger sample. We'll call that in here replication just because it's an easy word. Get a larger sample. So that's easy to do with the sampling, with coin flip. Okay, so go back. So, oops. So here's a distribution from a previous year, and what I've done here is graph the proportion of heads, right? You could think of it as the number of heads, but it's out of 10 flips, what's the proportion of heads that people got? 0.5, which we think is close to the true value. What do we, maybe 20% of the class got it, right? But the distribution is pretty broad, and if you flip a coin 10 times, you have a reasonable chance of getting something as far out as 0.3 or 0.7. If we now go to combine all of those flips from a single class, so now it's as though we flipped the coin 1,000 times or so, and then plot the distribution that we get over several years of classes. This is the number of classes. We see the distribution is now very close to 0.5. We don't get values way out at 0.3 or 0.7, right? So we understand that, right? More data, bigger sample, and the amount of noise in the average goes down. And we can show that graphically. This is a distribution of outcomes with small sample. And it'll be fairly broad distribution with large samples. And it'll do something like that. Or, may get even tighter than that. But as the sample increases, and that up arrow means increases, we close in on the true value. But we never fully eliminate sampling error. Except in some special cases that I don't want to talk about. Right, so So we can get ever and ever tighter around the true value by increasing the sample size more and more, but there's always going to be a bit of variation around it. So I'm going to make 4 points. And let me start with an example. Let's say we want the average SAT score for U.S. college students. My sample is 100 of you. Is replication present in this sample? So how many say yes? How many say no? About 50-50, that's fairly typical. So someone defend it. Defend either answer.
You're only taking one sample, so it's not replicating it over and over. In some ways you are because you're getting 100 students, and in another way you're not because you're only taking.
Okay, well you've just made both points I want to make. The answer is yes, 100 is more than 1, right? We'd get some information if we took one SAT score. Wouldn't be terribly useful, but I mean, it'd give us some idea, right? But we got 100, so that says there is replication present. There'll be less noise around the mean with 100 than there will be with 1. But as she pointed out, is replication absent? Yes. Only one class, only one university, etc. So the points are, 1, there are lots of ways to, let's say, have replication in a study. And anytime you see that there's more than one individual representing a particular sample, now let's say we wanted to do a male-female difference and I had one guy and one girl, there you could say there's no replication there. You need, multiple individuals from the same population, but we'll worry about that. Only one university? Now, you got to admit that is a very clear U. So you're going kind of a dimension beyond where I want to be right now. I'm not saying this is good. I'm just saying replication is present. Right? And that's kind of the first step to getting to what we want to achieve. So second, there are always ways in which a study is not replicated. You can always find ways, right? Even if it's a trivial one of saying, well, we only did that in the 1900s, or I guess we're now past that millennium thing. We haven't done it into the future. We haven't done it, over longer periods of time, etc. So you can always come up with ways in which a study is not replicated. And keep in mind, this is as simple as it gets. We're not talking about ideal design here. We're not talking about possible differences between UT and other universities. All that would be relevant, but I'm just trying to keep this to the bare minimum at this point. How much replication is enough? There is no set answer to this. It depends on the context and what you're willing to accept. If you are running a drug company and you're worried about the 1 in 3,000 extreme outcomes that could cost your company $500 million, you need very large sample size to convince yourself that you're safe from these problems. On the other hand, there are many purposes for which a sample of 10 or 100 might be enough, where you don't care about such, rare occurrences. We cannot say in advance that there's any set formula for how much replication is enough. And then the last point is kind of recognizing sampling error. Sampling error is measurable and usually reported. So formula exists to calculate sampling error and I put in the notes last hour, it's based on the sample size and actually depends on the data too, but don't worry about it because I'm not going to ask you this. I just want you to know that when you see something described as a margin of error, a confidence limit, or plus or minus something, which I'll do as a scribble, and that is not intended for you to be readable, right? But if you see you got a value plus or minus something, that is a description of sampling error. All these things refer to sampling error. Now, let me add then one more thing on this point is the following. Suppose you have two samples, right? And you have the mean of one and the mean of other, x1, x2. And you see the phrase to describe these is not significant or not significantly different, which I'm not writing out. What does that mean? Now you've talked enough. You've gotten too much right, basically. But this, well, the squiggle thing, but back up and be more general than that. When I say we got two samples, right, and we say they are not significantly different, what in very broad terms does that mean? What are we attributing? So they're not the same, right? We observe These could be SAT scores in 2 classes or whatever. I don't know what an SAT score is, but we're measuring something, and let's say it's 105 here and 113 here. The averages are in our 2 samples, but we say they're not significantly different. What does that mean about the observed difference between the 2 samples? Yeah. So it's another way to say it is the samples are different, but in terms of the underlying true averages or whatever, the differences are consistent with sampling error. So it means that what we observe is different between these 2 could be due to nothing more than sampling error. So we'll write that down. So most statistical tests are simply asking the question, are the observed differences consistent with sampling error? I want to talk now about the last type of error. Human and technical error. So these are things, these are screw-ups, right? And I'll write that down in a minute. But suppose I was to use these calipers to measure something, and I fail to zero it, right? And so you can tell there's a gap in there, at least I can. I turn the machine on, I do this reading, and I got a measurement that says 16.97, great. And I write that measurement down, and it turns out that, well, I hadn't zeroed the machine properly. In fact, it was not, should have been 0 here, and it's reading minus 0.87, so my measurement is that far off. That would be an example of human and technical error. So these are mistakes, blunders, machines not set correctly. Now we can always be on guard to avoid these. But we can never fully eliminate the possibility. And this is a big one in science in our daily lives. Fixing. I think I'm only going to list 2. A big one that you think is so obvious you wouldn't even list it is design procedures to reduce human and technical error. And this is all over our society, right? There's been a long history in aviation of them designing things so pilots make fewer and fewer errors. One of them is a checklist. Checklist, I don't remember when they came up with it, but I think it might have been in the 30s or the 40s, and they certainly was partly motivated by a crash at a display of different companies trying to sell airplanes to the military, And there was one super duper jet, and the pilot forgot to do something and crashed the plane. This was, while trying to convince buyers to do it. But there's so many things going on that they now design things so, the pilots have to actually punch buttons, I think, to make sure they've gone through their takeoff checklist. There are, I've been told that in the cockpit, devices that they pull for landing gear to come down actually look like a wheel, so they, make the association, etc. There was a case back from I don't want to say my childhood, but I don't know, somewhere in my teens that I remember hearing about. It was absolute tragedy. Headlines in the paper one day where a whole bunch of babies in a maternity ward had died, and it was like that. It wasn't gradual. Turned out the baby formula had been mixed wrong, and you just can't imagine the amount of horror this creates in people's lives that are affected by it, including the nurse who'd mixed the formula wrong. And what had apparently happened was that the protocol in place for mixing the formula was horribly flawed, right? So this is back when it wasn't one powder. You had to mix things, and you had to put in two different ingredients. One was sugar, one was salt. And of course, those things looked the same. The containers in which they were housed looked very similar, so it was a mistake waiting to happen. And this poor person, whoever did it, grabbed the salt thinking it was the sugar and put too much in the formula, and the baby's dehydrated, right? Had the protocol been in place that the two containers were colored differently, were labeled very clearly, this accident would not have happened. And there are all kinds of examples, but we know, right? We know there are procedures that we can put in place to minimize human and technical error. That's what fire drills are about. That's what all kinds of things we do are about, is to reduce the mistakes that we make with procedure. A second one that's on a much smaller scale and perhaps easier to understand is to use standards. Standards, a standard is an object of known value. So if the wrong value is reported for a standard, the mistake is immediately known. So what would be a standard for a thermometer? You've got a thermometer. It can be electric, it can be mercury, it can have the red stuff in it. What's a standard you can use to verify that it's giving you the right temperature? Okay, how do you know what room temperature is? Approximately, but let's say you want to get it to within a degree. You wouldn't necessarily know room temperature, but not bad. Body temperature. So what's body temperature supposed to be? 98.6 maybe Fahrenheit, and she said it in centigrade, but none of you heard it. What is it in centigrade? So what's our body temperature in Celsius? You're the only one that knows it in class? You know?
No.
You have a question, though.
No, I was saying that there's some variance there. If you do boiling temp, like boiling point, you know that there's an empirical boiling point of water. So like you might have body temperature variance for too long.
That's right. So that is a limitation of using body temperature. But if you went it across multiple people, if you got a weird reading and then you tried someone else and they got the same weird reading, you'd suspect that it was a thermometer. So 37 centigrade is body temperature. And it is helpful to know if you have a centigrade thermometer, you don't want to be at 98.6 on that. So you raised another one, boiling. So what's boiling? Okay, centigrade, it's 100, yay, and 212 on Fahrenheit. And then what's the other end of the spectrum? Freezing. So how do you get a standard at the low end? How do you actually achieve it? Yeah, no one last hour, I mean, it was stunning. So first of all, what's the freezing point of water? And on Celsius? 0. Okay. How, if you go in the average kitchen, maybe not nowadays, but go back 40 years, how can you actually accomplish this in a kitchen?
Take the temperature of a
Piece of ice. Okay. Okay, so ice can get colder than freezing, a lot colder, right? In fact, this is what happens up north, revealing my history here. If you put a container with water in a freezer, a glass container, for example, and it's full, it will do what? Break. And why is that? Because after it freezes and it gets colder, it expands. So you can get ice colder than freezing, but she said it right. What you want is a mix of ice and water that's come to equilibrium, and if you have both liquid and solid phases there, then that will be 0 degrees. Now, what about boiling? Not that you need to know this, well, if you're cooking. What's the one exception? Under what conditions is boiling 100 or 212? Sea level. So the higher you go up, what happens to the temperature? I mean the boiling point. Gets lower. Which means if you're cooking in Denver, if you're cooking at Telluride or someplace like that, high up in the hills, your boiling point's lower, and so instructions on recipes that say boil this long, you'll have to boil longer than that. There, a little bit of practical advice. So, ice, water, body temp, boiling water, and we're out of here. That's as far as I got last hour. So we're going to wrap up data and errors next time and move on to special cases. And I want the pennies back, so leave them somewhere on your way out.